It's not always easy to compute the limit of a sequence using the definitions as we have done before. Okay, but so that's why we have these rules that I'm gonna explain now. Okay, these are kind of computation rules for limits. Okay, so first proposition: suppose or let a sub n and b sub n be two convergent sequences. Okay, with limits a and b. So that means that a is the limit when n goes to infinity of a sub n, and b is the limit when n goes to infinity of b sub n, right? Well, the limit of this sequence, that's the sum of the two sequences, or the subtraction. So suppose we have a new sequence that's computed like this, okay? So this is just like when we summed functions. The new sequence is just the sum of the two terms, okay? Well, the limit of c sub n is just the sum of the two limits, okay? So just like I'm saying, if the limit of this, the sum is the sum, the limit of this of the subtraction is the subtraction. If the new sequence is, instead of the sum, is the product, okay, a sub n, b sub n, then the limit when n goes to infinity of c sub n is just the product of the limits of the two sequences, okay? And the same with the quotient between two sequences, just as long as this makes sense, okay? The sequence in the denominator is never zero, and the limit is not zero. Otherwise, it doesn't make sense, okay? This definition. Also true, the limit of a sequence that's exponentiated to a different one is the limit of the basis exponentiated to the limit of the exponent, and the limit of the logarithm of a sequence is the logarithm of the limit, okay? I'm not going to prove these ones, but they're very useful for our problems, okay? So just take them in and study them with care. Now, next rule is what we call the sandwich rule, okay? So suppose we have the limit of a sequence a sub n, it's called L, and another sequence c sub n is also have the same limit, okay, for all. And we have that for all n greater than a given threshold capital N, so given some number, or natural number, we have this bound. So we have the sequence a sub n is bounding from below this sequence b sub n, which is bounded from above by c sub n. Well, the limit then, the limit of b sub n is going to be equal to L. Okay, if you can think about it, if we take limits here, limit of a sub n, limit of b sub n, and the limit of c sub n, then this is L, okay, we have said, and this is also L, right? So this is L and L. So the limit of b sub n is between the same number, okay? So it's smaller or equal than L and greater or equal than L, so that means that this is L as well, okay? So remember that one, the sandwich rule. And then finally, the final rule for computation is that every monotonically increasing sequence bounded from above converges to some limit. Okay, and also the same, if a monotonically decreasing sequence bounded from below converges to some limit. So suppose you have any sequence that's this is 0, this is some value c, right? And this is a sub n. So we have, suppose we have something like this, and it's growing, it's growing, it's growing, and it's monotonically increasing, right? We know it's every term is going to be greater or equal than the one before. Well, if this sequence is bounded from above by any number, we know we can prove that this is going to be converged to a limit. Okay, the proof is actually very interesting, but we are not going to see it here. But just believe me that, right? That this is going to get closer and closer and closer and closer to a limit. It can't. Obviously, it can't grow to infinity, right? Because it's bounded from above, and it's not going to be alternating either. So it's because it's monotonically increasing. So it's going to be convergent to a given limit. Okay. And so, yeah, the proof for this is in the lecture notes if you're interested in.